Welcome to ReLu Radio, the podcast where we unpack the latest and greatest in machine learning research. I'm your host, Adam, and today we're diving into a fascinating paper titled Segment Anything from researchers at Meta AI. Joining me to break it all down is my co-host, Eliza. Welcome, Eliza.
Thanks, Adam. I'm excited to discuss this paper. It's a real game changer in the world of computer vision.
Absolutely. Let's start with the core concept. What's the big idea behind Segment Anything?
Well, Adam, the researchers at Meta AI have developed what they're calling a foundation model for image segmentation. It's a model that can segment literally anything in an image, based on various types of prompts. This is a huge leap forward in making segmentation models more flexible and generalizable.
That sounds incredibly powerful. Can you break down what they mean by foundation model in this context?
Sure thing. In the world of natural language processing, we've seen large language models like GPT-3 that can perform a wide range of tasks through prompting. The Segment Anything model, or SAM for short, aims to do something similar for image segmentation. It's designed to be promptable, meaning it can adapt to new image distributions and tasks without additional training.
Fascinating. So how does this compare to traditional segmentation models?
Traditional segmentation models are often trained for specific tasks or object categories. SAM, on the other hand, is designed to segment any object or region in an image based on various types of prompts, like points, boxes, or even free-form text. This makes it incredibly versatile and able to generalize to new scenarios.
That's really impressive. Let's dive into the introduction a bit more. What motivated the researchers to develop SAM?
The motivation came from the success of foundation models in NLP. The researchers wanted to bring that same level of flexibility and generalization to computer vision, specifically to image segmentation. They identified three key components needed for this: a promptable segmentation task, a model architecture that supports this task, and a large-scale dataset to train on.
And I'm guessing that last part was a challenge, right? I mean, where do you get a dataset large enough to train a foundation model for segmentation?
Exactly, Adam. That was one of the biggest challenges. Unlike text data, which is abundant on the internet, high-quality segmentation masks aren't readily available at the scale needed for a foundation model. So the researchers had to get creative.
Oh, I'm intrigued. What did they come up with?
They developed what they call a data engine. It's a clever iterative process where they use their model to assist in data collection, then use that newly collected data to improve the model, and repeat. This allowed them to create a massive dataset of over 1 billion masks.
A billion masks? That's mind-boggling.
It really is. And what's even more impressive is that they're releasing this dataset, called SA1B, to the research community. This could be a game changer for computer vision research.
Let's talk about the task itself. What exactly is the Segment Anything task?
The Segment Anything task is essentially a promptable segmentation task. The goal is to return a valid segmentation mask for any given prompt. This prompt could be a point, a box, a rough mask, or even free-form text describing what to segment.
That sounds pretty open-ended. How does the model handle ambiguity?
Great question, Adam. The key is in the requirement for a valid mask. Even if a prompt is ambiguous and could refer to multiple objects, the model is designed to return a reasonable mask for at least one of those objects. This is similar to how we expect language models to give coherent responses to ambiguous prompts.
I see. So it's not just about accuracy, but also about producing sensible results, even in uncertain situations?
Exactly. And this approach leads to a natural pre-training algorithm and a general method for zero-shot transfer to downstream segmentation tasks via prompting.
Zero-shot transfer? That sounds powerful. Can you give an example of how that might work?
Sure. Let's say you have a bounding box detector for cats. You could use SAM to perform cat instance segmentation by simply providing the detector's box output as a prompt to the model. No additional training required.
That's really cool. Let's dive into the model itself. How is SAM architected to handle this flexible prompting?
SAM has three main components: an image encoder, a flexible prompt encoder, and a fast mask decoder. The image encoder is a vision transformer that processes the input image. The prompt encoder can handle various types of prompts: points, boxes, masks, or text. Finally, the mask decoder efficiently combines the image embedding and prompt embedding to produce a segmentation mask.
Interesting. How does SAM handle the potential ambiguity we talked about earlier?
Great question. SAM is designed to be ambiguity aware. Instead of outputting a single mask, it can predict multiple masks for a single prompt. By default, it predicts 3 masks, which allows it to handle cases where there might be multiple valid interpretations of a prompt.
That's clever, but doesn't that make the model slower?
You'd think so, but the researchers put a lot of effort into making SAM efficient. The image encoder only needs to run once per image, and its output can be reused for different prompts. The prompt encoder and mask decoder are lightweight and can run in real time, even in a web browser.
Wow, that's impressive. How did they train this model?
They used a combination of techniques. The model is trained to simulate an interactive segmentation setup, where it's given a sequence of prompts for each training sample. They also use a special loss function that only backpropagates from the best of the multiple predicted masks, which helps handle ambiguity during training.
Let's talk about that data engine you mentioned earlier. How exactly does it work?
The data engine is really fascinating, Adam. It has 3 stages: assisted manual, semi-automatic, and fully automatic. In the first stage, SAM assists human annotators in labeling masks. In the second stage, SAM can automatically generate masks for some objects, while annotators focus on the rest. In the final stage, SAM generates masks automatically without human intervention.
That sounds like a really efficient way to scale up data collection. How many masks were they able to generate?
It's an astounding number, Adam. They collected over 1.1 billion masks from 11 million images. And what's really impressive is that 99.1% of these masks were generated fully automatically in the final stage.
That's incredible. But how did they ensure the quality of these automatically generated masks?
Great question. They used a combination of techniques. First, they only kept masks that the model was confident about, based on an IOU prediction. They also filtered for stable masks, which are masks that don't change much when you slightly adjust the threshold. Finally, they had human annotators verify the quality of a sample of the masks.
Let's talk about the resulting dataset, SA1B. What makes it unique?
SA1B is groundbreaking in several ways, Adam. First, its sheer size. It's 400 times larger than any existing segmentation dataset. But it's not just about quantity. The images are high-resolution, diverse, and importantly, they're all licensed and privacy-respecting.
Privacy-respecting? That's important. How did they ensure that?
They took several steps. All faces and vehicle license plates in the images have been blurred. The images are also downsampled to a maximum resolution of 1,500 pixels on the shortest side to further protect privacy.
That's good to hear. What about the diversity of the dataset?
They put a lot of effort into making SA1B more diverse than previous datasets. They analyzed the geographic distribution of the images and found that it covers most of the world's countries, with the top 3 countries coming from different parts of the world. They also looked at the distribution across income levels and found it to be more balanced than previous datasets.
That's really important for reducing bias in models trained on this data. Speaking of which, did they do any analysis of potential biases or fairness issues?
Yes, they did, Adam. They performed what they call a responsible AI, RAI, analysis. They looked at SAM's performance across different demographic groups, particularly in tasks like segmenting people and clothing.
And what did they find?
Interestingly, they found that SAM performed similarly across different perceived gender presentations and age groups when segmenting people. However, they did notice a bias when segmenting clothing. SAM performed better on clothing worn by people perceived as masculine.
That's interesting. Did they offer any explanations or solutions for this bias?
They didn't offer a specific solution, but they did emphasize the importance of being aware of these biases. They encourage users of SAM to be mindful of these limitations and to conduct their own fairness evaluations when using SAM for specific use cases.
Let's move on to the experiments. How did they evaluate SAM's performance?
They conducted a series of zero-shot transfer experiments across a wide range of tasks. These included single-point segmentation, edge detection, object proposal generation, instant segmentation, and even text-to-mask prediction.
Wow, that's quite a range. Can you walk us through some of these experiments?
Sure. Let's start with the single-point segmentation task. They evaluated SAM on a suite of 23 diverse segmentation datasets, ranging from everyday scenes to medical images and even underwater photos.
And how did SAM perform?
Surprisingly well. They compared SAM to state-of-the-art interactive segmentation models and found that SAM outperformed them on most datasets, especially when given just a single point as input. They also conducted a human study where annotators rated the quality of the masks, and SAM consistently received higher ratings than the baselines.
That's impressive. What about edge detection?
For edge detection, they evaluated SAM on the BSDS 500 dataset. Even though SAM wasn't trained specifically for edge detection, it performed remarkably well. It outperformed classical zero-shot methods and even came close to some supervised deep learning methods.
Interesting. How about object proposals?
For object proposals, they evaluated SAM on the LVIS dataset. They compared it to a strong baseline using a state-of-the-art object detector. Surprisingly, SAM outperformed this baseline on several metrics, particularly for medium and large objects, as well as rare and common objects.
That's really impressive. Did they try instant segmentation as well?
Yes, they did. They used SAM as the segmentation module of an instance segmenter, using bounding boxes from an object detector as prompts. While a fully supervised model outperformed SAM in terms of average precision, human raters actually preferred SAM's masks in terms of quality.
Fascinating. You mentioned text-to-mask prediction earlier. How did that work?
This was a really interesting experiment. They used CLIP, a model that aligns text and image embeddings, to enable SAM to work with text prompts. They found that SAM could segment objects based on simple text prompts like a wheel, or even more nuanced phrases like beaver tooth grill.
That's mind-blowing. It really shows the flexibility of this approach.
Absolutely. They also did some ablation studies to understand the impact of different components. They found that each stage of their data engine improved performance, and that scaling up the model and dataset size generally led to better results.
This is all incredibly impressive. As we wrap up, what do you think are the main takeaways from this paper?
I think there are a few key points, Adam. First, the idea of a foundation model for image segmentation is really powerful. It opens up new possibilities for flexible, generalizable computer vision systems. Second, the data engine approach they developed could be a game changer for creating large-scale datasets in other areas of AI. And finally, the release of the SA1B dataset and the SAM model could accelerate research in this field significantly.
Those are great points. Any limitations or future directions they mentioned?
Yes, they acknowledged a few limitations. SAM can sometimes miss fine structures or hallucinate small disconnected components. It's also not designed for tasks that require very high IOU, like detailed interactive segmentation. As for future directions, they suggest that composable system design, powered by techniques like prompt engineering, could enable a wider variety of applications than systems trained for fixed tasks.
Well, Eliza, this has been an absolutely fascinating discussion. The segment anything model really seems to be pushing the boundaries of what's possible in computer vision. Thank you so much for breaking it down for us.
It's been my pleasure, Adam. This paper is truly exciting, and I can't wait to see how researchers and developers will use SAM and build upon this work in the future.
And that wraps up this episode of ReLu Radio. Thanks for tuning in, everyone, And remember, in the world of AI, anything is possible, even segmenting anything. Until next time.